Okay, so let's start with some recap of the Dirac equation that we started in the last lecture. Dirac wanted to basically get rid of the sign ambiguity that one encounters in the dispersion relation, and therefore he chose to write down a first order dispersion relation in the energy. And if you write it in this particular form, alpha dot p times c plus beta mc squared, you realize that alpha and beta should be matrices. Of course, imposing the condition that E squared is equal to P squared C squared plus M squared C to the 4 gives you equations that alpha and beta matrices satisfy. And these are the equations: alpha I alpha j plus alpha j alpha I equals 2 delta ij, beta squared was 1, and alpha I beta plus beta alpha I equals 0. These are typically called anti-commutation relations. Remember, if you write down a commutation relation, you would have written down alpha I alpha j minus alpha j alpha I, whereas we are writing down a plus sign. So therefore, these are called anti-commutation relations. Okay. The simplest realization of algebra of this kind was polymatrices, but there are only 3 of them, whereas we want 4. So we realized that we need matrices which are bigger than 2 by 2 matrices. If you write that in the covariant form, then the anti-commutation relation looks like this: alpha mu plus alpha mu equals 2 delta mu nu. And this algebra is called the Clifford algebra. Okay. Now, if you impose additional hermiticity conditions that we would require the Hamiltonian to satisfy, those conditions would imply that alpha mu should be a Hermitian matrix, and alpha mu squared should be 1, which is the effect of the Clifford algebra equation, in fact, right here. Okay. And if you impose those conditions, you find that alpha I as well as beta are matrices with plus or minus 1 eigenvalue, and they are traceless. So if you have a matrix with plus minus 1 eigenvalue and traceless and non-vanishing determinant, because alpha squares to 1, would imply that the matrices have to be even dimensional. So if 2 by 2 matrices don't work, we will need 4 by 4 matrices as the minimal set to work with in 4 dimensions. Okay. Of course, if you are working in, say, 3 dimensions, then 3 by 3 matrices would do the job for us. Okay. Sorry, in 3 dimensions, 2 by 2 matrices would do the job for us. Excuse me. So the dimensionality of these matrices is dependent on the space-time dimensions, and it turns out that the dimension is 2 to the integer part of d by 2. So if you are working in 4 dimensions, then integer part of d by 2 is just 2, and that's why 4-dimensional. But if you are working in 5 dimensions, then integer part of 5 by 2 is again 2, and therefore again you have 4-dimensional matrices. Okay. For massless particles, however, you would have lower dimensional representations, and smaller representations would suffice in that case. Okay, so if you convert the dispersion relation by writing the operator formulation for energy and momentum, then the equation would look like this. And this equation, of course, requires psi to be a column vector because alpha and beta are matrices. Okay, so this 4-component column vector would be called the spinor. Okay, in fact, it would be called the Dirac spinor. Okay, we can, of course, make this equation look covariant by switching from alpha to gamma matrices by multiplying this entire equation by beta, and then the beta appearing in del by del t would be interpreted as gamma 0, and beta times alpha appearing in front of p would be interpreted as gamma I, and of course beta squares to 1, so there is no beta out here. If you do that, then gamma matrices have a little different anti-commutation relation that is typically represented by curly bracket as against the commutator bracket. And so this expression corresponds to gamma nu plus gamma nu, but now it will be equal to 2 times eta mu nu, unlike alphas, which was 2 times delta mu nu. Okay. Now, since we have chosen eta mu nu to be 1 minus 1 minus 1 minus 1, it tells you that gamma 0 squares to 1 and gamma 0 is Hermitian, whereas gamma I is anti-Hermitian and squares to minus 1. Okay. But once you do that, then you can write down this equation in a covariant form, and it takes the form like IH bar times gamma mu del mu or del by del x mu minus MC psi equals 0. Okay, and this is what is called the Dirac equation. Well, the previous one was also the Dirac equation, just that this is in the covariant form. One usually uses even more compact notation for gamma mu del mu by defining gamma mu O mu to be O slash, which is gamma 0 O0 minus gamma I OI. And so using that, you could just write down this as IH bar del slash minus MC. Okay, so that is where del represents del by del x mu, and del slash means gamma mu del by del x mu. Okay, and again the Compton wavelength was kind of appearing in this equation. Okay, the conjugate wave function to psi is actually written as psi dagger gamma 0, and this gamma 0 essentially takes care of this anti-hermeticity of gamma I. Okay, so that is one way of kind of explaining why you would want it this way. Okay, and you can write down a conjugate equation for psi dagger by just taking the Hermitian conjugate of the non-covariant equation and then multiply by beta squared. That means identity, but write that as beta squared everywhere, and you can convert that equation into an equation of this form, which can be written in a covariant form like this. Okay, this is all something we had done last time. Okay, so so what of course we want to do is, besides studying the Dirac equation by itself and its interaction with, say, electromagnetic field, we also want to take non-relativistic limit of this equation to find out what are the corrections to the non-relativistic Schrodinger equation when you do a reduction of a relativistic equation. So these are relativistic corrections that we are interested in. Okay, so to do that, we need a convenient basis, and the convenient basis is alpha matrices are off diagonal and beta matrix is diagonal. If you use that, then you find gamma matrices are off diagonal antisymmetric in terms of sigmas. So I shouldn't say they're antisymmetric because, you know, sigma 1 is, for sigma 1 it will be antisymmetric, for sigma 3 it will be antisymmetric, but for sigma 2 it will be actually symmetric matrix. So this form of writing is kind of misleading to think that all gammas would be antisymmetric, but they are not. Okay, and gamma 0 of course is the same as beta, so it remains as it is. Okay, fine. So as I said, psi would be a 4-component spinor, which would be written in terms of the polyspinor and its quote-unquote derivative. Okay, one could write down a current conservation equation, which is also something we had done last time, and that is basically you write down the Dirac equation and multiply by psi dagger, and subtract the Dirac equation for psi dagger multiplied by psi on the right. And if you do that, then you get the so there are like various terms, of which the mass term, which is MC upon h bar times psi dagger psi minus psi dagger psi, so that piece would just cancel out. Everything else you could kind of collect in this particular form. Okay. So once, of course, this derivative would act on psi dagger, once it will act on psi, and you will see that they kind of come directly from this expression. They are just a couple of lines of manipulation will bring you to this. Okay. So now this is a good form of conservation law, because the conserved charge in this particular case is psi dagger psi, which is manifestly positive definite. Okay, and so therefore you could try to, you could, besides giving kind of charge conservation condition interpretation, you could also give a probabilistic interpretation to this, because it is manifestly positive definite. And of course, if you normalize psi correctly, the highest value that it can take is 1. Okay, fine. Uh, but the current corresponding to this charge is taking the form like this, which is C times psi dagger alpha vector psi. And from that, if we could interpret C times alpha vector as kind of a velocity operator. Okay, so uh, but the problem with the velocity operator is that if you try to find out what are the eigenvalues of the velocity operator, then the eigenvalues are plus or minus C. Okay, so this is a very peculiar thing because this is a current corresponding to a massive particle, because our equation has an explicit mass term. Okay, so therefore you would have expected the velocity operator to return the eigenvalue which is smaller than C, but that's not what happens. What you get is plus or minus C to be the expectation value. And as I said last time, that there is this interpretation of the Dirac particle not actually traveling in straight line, but traveling along the light cone, not along the light cone, but traveling along 45 degrees, but zigzagging multiple times, so that effective path is time lag. Okay, so and that thing is called Zitterbewegung. But as I said, I will not get into that discussion. Okay, so you can write down a current in a covariant form. So we have a zeroth component written here. As you can see, you can multiply by beta squared or gamma 0 squared. Write down psi dagger gamma 0 as psi bar. Then you have a psi bar gamma 0 psi. That is this expression. And you can multiply by beta squared here or gamma 0 squared here. Soak up one gamma 0 in psi dagger to write down psi bar, and the other one beta alpha can be written as gamma. Okay, so if you write down these two pieces together, then you write down J mu is equal to C times psi bar gamma mu psi. Okay, and that is a covariant form of the current, and del mu J mu is equal to 0 is the conservation law. Okay, so let us try to understand the velocity operator a little better. And we, I think, stopped around this time, last time. Okay, so the velocity operator and the force operator for the free particle are written in this particular form, that dr by dt, which is like a velocity, is the commutator bracket of r with h. Okay, this is just this is the same as Hamilton's equation written now for the quantum system operator form. Okay, but we know what this object is. Hamiltonian contains a c dot c times alpha dot del piece, and it also contains beta mc squared piece, right? Because maybe I'll split the screen, which will be easier. Yeah. So if you look at this equation, then or maybe not the conjugate equation. Let's look at the original one. Yeah. So if you look at this equation, IH bar del del t is like a Hamiltonian, right? So that is written in terms of these quantities. Okay. So therefore, you can kind of quickly see that I by H bar acting on this the remaining piece is basically the Hamiltonian with the minus sign, because IH bar del del t minus H is equal to 0 would be the kind of equation that you would want to write down. So minus of this is Hamiltonian. So if you multiply by I by H bar, you basically get C times alpha dot del, because that will cancel out this piece. Okay. Beta times mc squared will of course commute with r, because there is no differential operator kind of object. So therefore HR commutator is basically this commutator. Okay. Now this, of course, the uh, gradient operator would act on r exactly when the appropriate derivative clicks. Okay, and that would give you C times alpha. Okay, and that is velocity. That is velocity because it is dr by dt. On the other hand, if you take dp by dt, which is what you would call force, or which would be related to acceleration, then you'll find that that commutator would vanish because del commutes with the p operator, and there is no non-constant pieces on which a p operator would act on. Okay, so this is a nice thing. We are looking at a free particle which does not experience any acceleration or any force. But a velocity operator is the one that we interpreted some time ago, c times alpha, okay, which is what comes out if you try to look at this equation. Okay, now the fact that there is no force acting on this, okay, is not directly congruent with the time variation of the velocity operator itself, because velocity operator is proportional to alpha. So if you look at time variation of velocity operator, you again use the same relation, I upon h bar times commutator of h with the velocity operator. Okay, sorry, there was no need to write c there, but okay. And you can see that this object is c times alpha, and that alpha wouldn't commute with this alpha because kind of they are written in terms of Pauli matrices. They don't have simple commutation relation. They have simple anti-commutation relation. Similarly, these alphas wouldn't commute with beta also. So this quantity is not going to be 0. Okay, so you find that the velocity is not constant. Okay, now that is one of the reasons why this Zitterbewegung interpretation says that you would go along the light cone in one direction, then you switch and go around the light cone in the other direction, and like that. So you keep going at 45-degree this thing, but flipping the direction. And if you kind of at very small intervals, if you keep flipping the direction, then of course ddt of the velocity operator wouldn't be 0, simply because there are cusp points across which the velocity operator is changing its direction. Okay, that is how Dirac actually tried to interpret this equation, and till date that is how it is being interpreted. Okay, fine. But coming back to the relation of this quantity with say the momentum operator, then we see that the velocity operator is naturally related to the rate of change of position operator. Okay, but it is not so naturally related to the momentum operator. So you wouldn't write down the momentum operators as mass times the velocity operator. Okay, because that is not the way it is working out, because dp by dt is 0, but d velocity operator by dt is not equal to 0. Okay, so the relation is not clearly straightforward at the quantum level. But at the classical level, you could still kind of try to make sense of it, and we will do it in a moment. Okay, so there's some curious thing that you could do. You can see that the momentum, you can get the momentum operator if you replace the commutator here by anti-commutator. Okay, so if you anti-commute dr by dt with the Hamiltonian, then alphas have nice anti-commutation relation. Remember, alpha mu is delta mu nu. So therefore, if this anti-commutation relation clicks, then it will give you the p vector back. And if it doesn't click, it will of course give you 0. Okay, so this anti-commutation relation actually gives you the momentum operator. Okay, so it's a kind of curious thing that the velocity operator commutator with Hamiltonian doesn't work, but the anti-commutator does. Okay, fine. So you could ask a question that suppose I have energy eigenstates, and if I want to compute the expectation value of the velocity operator, okay, then what is it that you would get? And what you get in that case is a quantity like this, which is the expectation value of pc squared upon E. Okay, so it is only in the expectation value sense, in the semi-classical sense, that you would relate a velocity operator with the momentum operator, but the relation at the operator level is not so simple. Okay, so let's try to understand the velocity operator further. Okay, so to understand this, we can try to see what is the, how does the velocity operator behave. Okay, so for example, remember we have said that alpha mu anti-commutator is delta mu nu, but alpha mu commutator is not so simple quantity. Okay, you actually have to write down alpha mu explicitly in the matrix form and actually study their commutator. Okay, we will later study the commutators of gamma matrices, for example, but velocity operator is written in terms of alpha matrices. And if you try to study the commutators, then first thing that you will notice is that different components of velocity operators do not commute with each other. Okay, which is quite different from what happens with different components of the momentum operator. Like px commutes with py, and similarly with pz. Okay, but Vx does not commute with Vy, in fact, okay, because alpha matrices that appear in the definition of the velocity operator, alpha x, alpha y commutator is not zero. Okay, so therefore, it's a very curious object that it does appear as a velocity operator, but the different components of the velocity operator in the operator form do not commute. Okay, so let's try to.
But this is also kind of present in the presence of magnetic field when we study
Yes.
and studying the equation.
Yes, absolutely. If
Yeah,
you have external magnetic field, then the momentum in x direction and momentum y direction don't commute. Okay, generalized momentum.
But now this is happening for a free particle only.
Yes, the problem here is it is happening for a free particle, exactly. Okay, so that is why it seems a bit counterintuitive. Okay.
And also this V operator,
yeah,
I am not sure how we are, I mean, relation with dr by dt is fine.
Yeah.
Is that itself enough reason to call it something like the kinetic momentum or kinetic velocity?
Well, I mean, this expression is correct, right? I mean, dr by dt as a Hamilton equation. Okay.
Yeah.
So that is the one which gives you this c times alpha, right? And this way you are kind of essentially forced to interpret that as a velocity operator, right?
Yeah. Okay.
Okay, so let's try to kind of understand, many of these puzzles are kind of related to each other. So let's try to understand how the angular momentum operator works out. Okay, so angular momentum operator is written as r cross p. Okay, this is how we define angular momentum. So let's try to see how the time derivative of the angular momentum operator would work. Okay, now remember, we want the angular momentum to be conserved. Okay, so therefore if you write down I upon h bar times commutator of h with L, we would expect the answer to be 0. Okay, now let's look at that here. Okay, so if you write down L to be r cross p, then only relevant term would be alpha dot p from the Hamiltonian. Okay, this is this alpha dot del piece. The other piece is not really important. It would just kind of commute through r and p. Okay, so therefore you can just compute this. If you compute this quantity, then you will find that this gradient would act on r, wouldn't act on p. Okay, and whenever it will click, it will give you the equation which is alpha dot p. Okay, but this c times alpha dot p, oh wait a minute, I should have got alpha cross p, sorry. Okay, because sorry, this is a mistake. It should be c times alpha cross p. Okay, because of this cross product. Okay, and but c times alpha is a velocity operator, right? So you get an answer that del L by del T is a velocity operator cross P. Okay, now had the velocity had there been a simple relation between the velocity operator and the momentum, then we would have said that this answer is 0, because momentum operator and velocity operator, if they are parallel, which is the usual case, P is equal to m times P. Okay, then in that case this is naturally 0. Okay, but that's not the case now. Okay, so you get this answer. This is, forget about velocity operator. If you just look at this alpha cross P expression, then you will immediately see that then you'll immediately see that this quantity c times alpha cross p is actually non-zero. Okay, so what we find is that the angular momentum in this particular case is not conserved. Okay, fine. So it's the same interpretation that I was just giving, that velocity vector is different from the angular momentum vector. Okay. So the question is that therefore is what is the way out of this thing? We know that angular momentum is conserved, and in the Dirac formalism, it looks like the angular momentum is not conserved. Okay, so now we of course know experimentally that angular momentum is conserved. So we can ask a question: can we modify the equation so that the angular momentum conservation law is recovered? Okay. So that's the only way we could kind of reconcile whatever we see with in the experiment with the Dirac equation. So let's do the following thing. Let's define a new angular momentum J, which is L plus S. Okay, where S is the spin degree of freedom, or which is what is called the intrinsic angular momentum of the particle. Okay, and the total angular momentum J is a vector sum of the orbital angular momentum L plus the intrinsic spin angular momentum of the particle. Okay. Now, if you do that, then we can ask a question: can we demand that the total angular momentum J is time independent? Okay. So dJ by dt is 0. Okay. So, so of course, for that we have to find a form for S such that the commutator of S with H would cancel the commutator of L with H. Okay, I wrote it the other way around, but it's the same order. If you are looking at HS commutator, then it should cancel the HL commutator. Okay, so let's choose S to be H bar upon 2 times Pauli matrices diagonally. Okay. Now remember, sigmas which are Pauli matrices satisfy the following relation: sigma I sigma j is equal to delta ij plus I times epsilon ijk sigma k. Okay. And we also know from non-relativistic quantum mechanics that the eigenstates of the Pauli matrices are up and down spin states. Okay. So let's try to kind of see how this operator varies as a function of time. Okay, so ds by dt is, so notice that it is h bar by 2 factor. So you can write down this expression h bar by 2 times this matrix. Okay. Sorry, h bar by 2 times this matrix times c times p times this alpha matrix. This is alpha dot p, which is a part of the Hamiltonian. Okay, sorry, it is looking a bit messy, but let me explain slowly. I by h bar is the piece that we have been using always outside the Hamiltonian. I by h bar times the commutator of Hamiltonian with some operator. Okay, so I by h bar is that piece. This is alpha matrix, alpha dot p, which is part of the Hamiltonian. The factor of c I have pulled out here, and this is the operator s, which is h bar by 2 times s. Okay, now what we have to do is to basically look at this commutator. Okay, so you can kind of write down that in a piecemeal fashion. Okay, expand this matrix, and you will find that h bar of course cancel. You get ic upon 2, and this commutator will look like, so you can take say p inside, you can write down this as sigma dot p at both places, and this commutator just sits off diagonally as a commutator of sigma dot p with sigma. Okay, fine. So sigma dot p with sigma commutator will give you a sigma cross p. Why? Because sigma I sigma j, if I and j are same, then it will give you delta ij. But in the commutator, if I and j are same, that commutator would vanish. Okay, so therefore I and j same is not relevant for the commutator. If I and j are not same, then they would give you sigma k, but then there is a epsilon ijk sitting around. So therefore, what you would get is sigma I pi sigma j commutator will give you epsilon ijk p sigma k with pi, which is like a cross product. Okay, because epsilon ijk with two vectors would give you a cross product. So that's how you end up with this cross product. Okay, but then you get minus c times sigma off diagonally, which are alpha matrix, and therefore you get an answer minus c times alpha cross p. Okay, that is the answer that you would get. so spin is also not conserved. But notice that exactly C times alpha cross P is a factor that you get here, modulo my typo here, but with a plus sign. So this is a plus sign and this is a minus sign. Okay. So therefore, if you look at J, which is L plus S, then you write down J, which is time variation of J to be del L by del T plus del S by del T, which will give you C times alpha cross P minus C times alpha cross P, and therefore that answer would be 0. Okay. So what you find is that the total angular momentum of this particle is conserved, but orbital angular momentum or spin angular momentum individually are not conserved. Okay. Now, of course, you may have a situation in which the orbital angular momentum has 0 value. Okay. In that case, of course, the spin would be conserved because the total angular momentum is conserved. Okay. But in general, in the operator form, what you find is that only the total angular momentum is conserved. Okay. Now remember that S is written in this particular form, and you know Pauli matrices have eigenvalues plus or minus 1, right? So therefore, S would have eigenvalues h bar by 2 with plus or minus sign. Okay, 2 eigenvalues are h bar by 2, 2 eigenvalues are minus h bar by 2. Okay, so clearly, if you have eigenvalues plus or minus h bar by 2, that would imply that the Dirac particle would have spin half, because those are the kind of projections of the spin half particle. Okay, so what do we find? We find that if you impose the conservation of angular momentum, then the spin degree of freedom is a natural consequence of demanding conservation of angular momentum in the Dirac formulation. Okay, contrast this with what we did in say Schrodinger equation. In the case of Schrodinger equation, we introduced the Pauli spinor by hand. You could have chosen not to introduce Pauli spinor. For example, when you study, say, a harmonic oscillator or even hydrogen atom, you don't write Pauli spinor. You just solve the Laplacian acting on the Schrodinger equation minus the Coulomb potential is equal to whatever is the energy. Okay, and you just solve that problem without even worrying about whether the Schrodinger wave function was one component or two components. You treat that as one component object, and at the end of the calculation, you say, no, it is an electron and it has to have up and down spin, and you just attach a Pauli spin, or whether which would be either 1, 0 or 0. Okay, which is a totally ad hoc construct. As against what happens in the Dirac formulation is that you don't have a choice. Okay, if you say that the total angular momentum of the system is conserved, then you are forced that the system has to have the particle has to have intrinsic or spin angular momentum to be half. Okay. Now, this intrinsic spin degree of freedom did not exist in the case of Klein-Gordon equation. In fact, we didn't even need this kind of expression when we studied Klein-Gordon equation. Okay, so in that sense, Klein-Gordon equation represents a particle whose intrinsic spin is 0, whereas Dirac equation represents a particle whose intrinsic spin is half. Okay, so any questions at this point?
So
Yeah.
I would like to somewhat see how psi, the spinner itself, and how gamma transforms under when we do a Lorentz
Yes,
transform.
we will do it in the class today.
Okay.
I wouldn't do how psi transforms, but we could do it at some point later, maybe. So, in some sense, we'll have to do some Lorentz algebra representation theory kind of stuff. So, but I think you will do that in math method course, no?
I don't think so. I
I
don't
see.
know.
Okay, let me check actually. Yes, but we will. I mean, I will not derive, but I'll show how the gamma matrices would transform. Okay. Okay, so so main point here is to say that besides the, so of course that the Dirac particle has spin half is also part of the result coming from Lorentz algebra representation theory. Okay, that also one could kind of check. But this derivation that you actually need spin half as the intrinsic angular momentum of the particle is independent. Okay, you could have said that like, okay, I don't care about what is the Lorentz algebra representation theory is telling me. Can I really figure out whether this particle has spin half or not? And the answer is yes, you would get it by just demanding that the angular momentum is conserved. Now, of course, you could say that like angular momentum is conserved is also a consequence of Lorentz algebra. And the answer is in a way yes. Okay. But at least you are not kind of, handing over the spin degree of freedom to the representation theory, but you are kind of deriving that as a part of conservation law. Okay, so it is related, but still a bit of a different derivation. Okay, fine. We can also define another quantity called helicity, and helicity is written as J dot P, and but J dot P is essentially S dot P because J is L plus S and L is always orthogonal to P because L is R cross P. So if R and P are in a particular plane, then L is perpendicular to that plane. So if you take a dot product of L with that, with any of the operators in that plane, of course it would be 0. So what you get is that J dot P is basically the spin uh, having an inner product or dot product with P. So this operator basically tells you that it measures the projection of the intrinsic spin in the direction of the momentum. Okay, so if you have a particle with spin, so you are not looking at say a scalar particle, but you are looking at say a spin or a fermion, like the Dirac fermion kind of object, or you may be even looking at vector particle like the gauge field. Okay, like electromagnetic field. Okay, mu. Then this kind of operator is well defined, and it will tell you what is the projection of the spin degree of freedom in the direction of the momentum. Okay, so it may project in the direction, it may project opposite, or it may be perpendicular to the momentum. Okay, but of course, if you define a quantity like this, then one thing that you notice is that like if the spin is pointing in the direction of momentum, if I say something like that, then you could always say that like, okay, I can always go to a frame in which the momentum switches its direction. Okay, you can just get into a boosted frame, and the velocity of that frame with respect to my frame is larger than the kind of velocity that this particle would have. Then the direction of momentum is reversed. And if I say that the helicity is positive, you would say that no, helicity is negative because spin is pointing opposite to the momentum. Okay, so helicity in that sense is not a very well-defined quantity for massive particles, but it is a good quantity for massless particle. Okay, it is in fact conserved because there is no Lorentz frame in which you could change the direction of the momentum of a massless particle. Okay, so for example, if you are looking at photon, okay, which is given by electromagnetic field mu, and since that electromagnetic field carries a Lorentz index, it is a spin 1 object. It has a spin projection, and that those projections, whatever they are, okay, whether in the direction of momentum or opposite, are Lorentz invariant quantity. You cannot go to any other frame to change the projection of the spin. Okay, so this is one interesting operator. Uh, in particular, in particle physics, it has an interesting role to play. Okay. Now remember one thing, that although it is a good quantity, it is a conserved quantity for massless particle, it would be a good quantity for even massive particle if they are moving at very high velocity. Okay, so as I was saying in one of the classes earlier, that suppose you are looking at electron with uh, total energy of the order of like uh, 10 to the 3 giga electron volt, like about 1 TeV. That is the kind of energy an electron has. Now 1 TeV energy for half a MeV electron rest mass is a huge amount of energy. It's like 6 orders of magnitude larger than its rest mass. Okay, so for all practical purposes, you could think of electron with that kind of energy moving with the speed of light. Okay, so it may be, of course, 0.99999 times speed of light, but for all calculational purposes, you can ignore that error and you can just treat that as C. Now, if you have a situation like that, okay, then you say, when you treat electron as massless, then helicity would become a good operator. Okay, so if you are trying to study a system or a configuration in which there is a particle which decays, okay, imagine that particle decays into two particles, okay, and one of the particles is, say, electron, and electron typically has huge energy. If that particle is very massive, it will provide large amount of energy. A two particle decay would imply that both the particles will carry equal amount of momentum, because the initial particle, if it is at rest, then both the particles will carry equal and opposite direction momentum. In that case, you could essentially treat electron to be massless, okay, and assume that the helicity is conserved. It may give a very strong constraint on whether a particular decay happens or not. Okay, so in that sense, this is a very important quantity in explaining why certain uh, decays which should be easily possible actually do not happen. Okay. Okay, so let's try to solve the Dirac equation. We would kind of write down answers solution. Uh, Remember, we are trying to solve the free Dirac equation, and if you are looking at the free particle equation, then typically you would use a plane wave basis. Okay, so if you use a plane wave basis, then you would write down psi alpha. So okay, so let me just first say this, and then I'll kind of tell about what I am doing. So you can write down psi alpha x as omega alpha 0 times exponential of I times p dot r minus et. Okay, so x is basically a 4 vector written as t comma r vector. Okay, alpha are the components of the spinors. Remember, psi was a 4 component spinor, so alpha take 4 values. Okay, it's a bit unfortunate that we are using alpha as an index to denote spinorial values, but typically what one does is that among the Greek letters, you use mu, nu, rho, sigma kind of letters to describe the space-time vector quantities, like del by del x mu, or x mu, or a mu. That will be used as mu, nu, rho, sigma, which are called middle Greek indices. And beginning Greek indices like alpha, beta, gamma would be used for spinorial variables. Okay, that is a kind of convention one uses. Now, this convention, of course, we will not use in general relativity, because you need so many indices that uh, at some point you don't make distinction between alpha, beta, and mu, nu, really. Okay, so uh, in different lectures, I will have different convention. It's a bit unfortunate, but yeah, we'll have to live with it. Okay. Now, in fact, in general relativity, when you try to study fermions, then you do a little different trick. You use small beginning Roman letters to define a spinor. So you would actually call that psi A. Okay, ABC would be used for spinorial indices. But okay, we can keep that aside right now. Okay, fine. So now what we could do is that we can choose this. When I say omega alpha 0, I mean that omega alpha does not have any explicit dependence on coordinates. Okay, it could depend on other quantities, like it could depend on momentum, energy, but not on r and t. Okay, that's what I mean by 0. Okay, so when you substitute this into the Dirac equation, which is right here below, okay, then del by del t or nabla would act on only this exponential piece, because omega is not a function of that. Okay, so when it acts on these quantities, they would pull out P and E, and you get an equation which looks like this. Okay, now this is of course the beginning of the Dirac equation, right? You wanted E is equal to C times alpha dot P plus beta MC squared, okay, which is what you have recovered by using the plane wave basis. Okay, but now you have recovered that with omega alpha multiplying that to be equal to 0. Okay, and we want to get, of course, non-trivial solution to this equation. Trivial solution is, of course, to say that omega alpha itself is 0. Non-trivial solution is to set this quantity to 0. Okay, so now, of course, if you set this quantity to 0, it is the original dispersion relation that you have. Okay, but that's not what we want to do. What we will do is we'll write that expression explicitly. Okay, and it will look like this. Bad notation. Okay, this should have been sigma dot p. Okay, I should start correcting this stuff. Okay, I will correct it. By the way, I am trying to correct the typos in the notes. Please do take a look. In case I have not managed to correct a few, please write to me about them. Okay. I have been trying to keep track of them, but like there are times I have forgotten a few. Okay. Fine. So that when you write this in an explicit matrix form, then it would appear to be E minus MC squared, because remember beta was diagonally 1 minus 1. So that's why minus MC squared and plus MC squared diagonally. Off diagonally, this should be polymetric. So you have minus C times alpha dot P minus C is coming from here. Okay. So sigma dot P and a sigma dot P. And omega, which is a 4-component spinor, I write that in terms of two component spinor. Okay, phi is a 2-component polyspinor, and chi is also 2-component polytype spinor. Okay, so okay, let me not use the word poly because polyspinors are very specific, 1, 0 or 0, 1. We have just written them as 2-component spinors. Okay, so 4-component spinor is decomposed into phi and chi. Okay, so since I have copied it from here, the error has propagated. This thing. So what we'll do is that non-trivial solution, of course, would correspond to this quantity being 0. This is like solving this secular equation kind of stuff. Okay. The determinant is, of course, E squared equals P squared C squared plus M squared C to the 4. And there we are back with plus or minus sign. Okay. So although we wanted to avoid that sign, you are back with that sign again. Okay. So therefore, even the Dirac formulation does not help us get rid of the negative sign solution, and we have to essentially give the interpretation to what that negative sign is. Okay, so we will probably not spend too much time on that because we know that the negative sign solution is actually a antiparticle solution. Okay, so antiparticle with positive energy is same as the particle with negative energy. Okay, that is how this negative energy solution would be interpreted. Okay, fine. So, but we can kind of ask how would the solution look like. Okay, so we have this W sitting here, which is written in terms of phi and chi, and if the energies are this, suppose you choose a plus sign, okay, then you can ask what should be the form of phi and chi such that you get this solution with a positive sign. And the answer is that omega plus, which is a positive energy spinor, is some normalization factor, which we will determine soon, times phi, which is the 2-component spinor, and the chi, which is the lower spinor, which is written as C times sigma dot P upon E plus plus MC squared. By E plus, I mean the energy with positive sign here. Okay. And phi could be any one of these two spinors, which are the poly spinors. It could be 1, 0 or 0, 1. Okay. Now notice that the lower component is also 1, 0 or 0, 1, but it is multiplied by sigma dot P upon E squared is E plus MC squared. Okay. For positive energy, E plus MC squared is always greater than sigma dot P. Okay. So therefore, this component is smaller than 1. if this component is proportional to 1, this component is smaller compared to that. Okay, so therefore for positive energy solution, you interpret upper two component to be large components and lower two component to be small components. Okay, so particularly if you take non-relativistic limit, then of course, P is small compared to the rest mass, and therefore this quantity is small. Okay, that is how we will interpret. Okay, fine. If you have negative energy solution, then the role is opposite. The chi's are 1 or 0. Okay, 1, 0, 0, 1. And phi is written as sigma dot p divided by E minus mc squared. Okay, and of course denominator E minus is of course negative, so therefore this quantity is also, magnitude of this quantity is still larger than the numerator, and therefore this component is smaller than this component. Okay, so in the non-relativistic limit, again you will ignore this piece. Okay, so a particle degree of freedom in the non-relativistic limit is only 2 component. Okay, the lower 2 components are small. Antiparticle degree of freedom is again 2 components, which are lower components, and upper 2 components are small. Okay, so so if you try to take the non-relativistic limit of this system, then you would essentially interpret omega plus to be A times phi 0, whereas omega minus to be A times 0 chi. Okay, so that is the reason why in the non-relativistic limit you have 2 component spinors and not 4 component spinors. Okay, any questions at this point? Okay, if not, then we can proceed ahead. Okay, so if you want to determine particle density, which is related to psi dagger psi, then we should remember one thing, and that is that if you want to write down a quantity like this, then it has to be defined with respect to the volume, and the volume itself undergoes Lorentz contraction when you do Lorentz boost. Okay, so therefore you have to normalize psi dagger psi in a correct way. If you don't normalize it in correct way, then the psi dagger psi computed in one frame may not agree with psi dagger psi computed in another frame, even if you do an integration over entire space-time. Okay, simply because in the boosted frame, due to Lorentz contraction, the volume would change. Okay, so in other words, psi dagger psi should be written with appropriate normalization. Okay, so the normalization that we require is that we write psi dagger psi is equal to mod E by mc squared. Okay, fine. So this is something we had talked about earlier also, that you need such factor to compensate for the Lorentz contraction result. Okay, but we know that psi dagger psi is actually written in terms of this normalization A. Okay, so remember, you look at any of these expression, you can choose this or you can choose this, doesn't matter. Okay, you can take that and you plug it in. If you choose phi or chi, whatever, uh, the phi dagger phi would just give you 1. Similarly for chi. Okay, so therefore, when you write down psi dagger psi, which you want it to be mod E upon mc squared, if you substitute the spinor, then you get that to be mod A squared times 1 plus c squared p squared upon mod E plus mc squared whole squared. Okay. Now, if you had taken a negative energy solution, you would have gotten minus signs at both places, but when you square it, doesn't matter really. So you get the same answer. Okay. You want to set this quantity to be mod E upon mc squared. So you can expand this, take the common denominator, square this quantity upstairs. So you get E squared, m squared c to the 4, and a cross term, which is 2 mod E mc squared plus the c squared p squared piece. Okay. But you can check that these pieces you can kind of collect together. You get m squared c to the 4 plus c squared p squared is same as e squared. So you get 2e squared. Okay, so you can write down that as mod e times mod e plus mc squared. Okay, which you can kind of use to cancel some piece. Okay, and one of the term in the denominator and the other term survives. Okay, and so you get mod a squared times 2e, 2 mod e upon e plus mc squared is equal to e by mc squared. Okay, so let me say it again. You have this denominator p squared. If you look at the numerator piece, okay, you have a e squared sitting around here, m squared c to the 4 plus p squared c squared piece here is again e squared. So you get 2 times e squared plus 2 mod e mc squared. So you can take mod e common and then you get mod e plus mc squared multiplied by 2e. Okay. So that mod e plus mc squared can get rid of one of the piece in the denominator and you are left with 2e, 2 mod e divided by only one copy of this denominator. Okay, that multiplied by mod a square should be equal to this. Okay, clearly 2 mod e, one of the mod e will cancel, mc squared goes on the other side and mod a squared is equal to 2 mc squared upon one copy of the denominator is equal to 1. Okay, that tells you that mod a should be square root of that quantity inverse. Okay, so that is how you derive the normalization of the spinor. Okay, fine. So once you choose this normalization, then you can kind of do a small exercise. You can show that with this normalization, psi bar psi is equal to plus or minus 1. Okay, so that is a kind of simple check that you could do. Okay. So any questions at this point?
Would you say why we fix psi dagger psi to be mod e by mc square again?
Oh, okay. So, so what I'm saying is that, like, you want to define the total charge or total probability density of a particle to be equal to 1 in the full volume, right? Is that okay?
Yeah.
So integral dv, where v is the volume, psi dagger psi is equal to say 1. Okay, with respect to a proper normalization. Okay, so if you choose a to be whatever that. Okay, don't worry about what a is, but suppose you define this to be 1. Okay, that is how it is normalized. Okay, then this is in one frame. Suppose this is in my frame. Okay, if your frame is boosted with respect to my frame, okay, then the lengths that I would measure, okay, are different from the lengths that you would measure. Okay, so I would see that you will notice a length contraction. Okay, so the volume that I would measure is larger than the volume that you would measure. Okay.
Yeah.
So if we have to agree with our calculation, then I would have to do the following thing, that whatever volume you would measure, I should multiply that by a gamma factor. Okay. And then check that with my result. Gamma is the gamma factor, which is 1 over, which is whatever, 1 over square root of 1 minus v squared by c squared. Okay. If I multiply by that factor, then it would agree with my result. Okay. But now you see mod e by mc squared is precisely gamma factor, right?
Why do we need to put mod e? Why not just e?
Oh, because I can have positive energy solution or negative energy solution. Okay. But in either case, if it is in the boosted frame, it should just give me a gamma factor. Okay. So that is by mod e. So saying that, like, it doesn't matter whether you look at particle or positive energy particle or negative energy particle. The Lorentz contraction effect would be soaked up if you write it in this form.
Okay. Okay.
Okay. So that is how. So this is basically, a bit fancy way of writing just gamma, because E is equal to gamma mc squared, where m is the rest mass. Okay. So mc squared will cancel, give you gamma essentially. But Writing it in this way fixes your normalization correctly. That's all. Okay. Any other question?
So
Yes.
this negative energy particle describes an antiparticle, right?
Yeah, negative energy particle is a positive energy antiparticle. Okay.
So why do we want rho to be positive always? Initially, when we were doing Klein-Gordon equation,
Yeah.
and we got a rho that was positive as well as negative for some value.
That's right. Yeah.
And we interpreted it as giving us the charge density of a particle.
Yes. Yeah.
So why are we not doing it here?
Because we are trying to give a probability. We are trying to give a probabilistic interpretation. We are saying that this is a probability density, and that's why it cannot be negative.
Yeah. Okay. But what would rho describe? Probability density of a particle or an antiparticle?
After this is the probability density of the particle. Okay. So whether the particle is a positive energy or negative energy doesn't matter. It's the probability density of particle of any energy.
So it is kind of adding up those probability densities.
Yes. Yes, exactly.
Okay. And it's still relativistically invariant. No,
Yes,
it
I
is
mean,
not invariant because it is like
no,
side is not.
side is not relativistically invariant. It has to kind of correctly kind of compensate for.
I put it wrong way. I was saying if we were describing the charge density of particle as well as antiparticle,
Yeah.
The antiparticle has negative charge from the positive charge, from the particle.
Yeah.
So we should not write it as rho, right? It should be some different value.
No, why?
Because it can be positive as well as negative. Uh, if you were writing charge density.
Yeah. But the charge density will not. Yeah. So charge density will not be written this way. Charge density will be, of course, expression is the same, but it will be multiplied by the charge. Okay, so it will be written as E times psi dagger psi. Okay.
But that would not do anything. It will always be positive.
No. Because E will flip sign for particle versus antiparticle. It will flip the corresponding charge density.
You mean an operator?
E is the electric charge.
Then you are just multiplying the constant with side over side. Right?
Absolutely, yeah. But that constant is an operator in some sense. When it acts on a particle state, it returns one value. If it acts on antiparticle state, it returns opposite value.
So it should be like some kind of expectation value of a charge operator.
Exactly.
Psi dagger E psi.
Yeah. It is sandwiched between the psi dagger psi. If that's what you want to know.
Okay.
Indeed.
Okay.
Yeah. So in fact, when you will do particle physics, you will typically sandwich that as a matrix operator, because you may be doing a matrix gauge theory, whereas electrodynamics is just a single scalar quantity. So because it's a single scalar quantity, you could have written it in sandwich between or outside, but physically it actually is being evaluated as an operator and therefore sandwich inside.
Okay.
Any other question?
Could you go a couple of slides ago?
Yeah, sure.
We just calculated the energies here.
Here or further up?
Below.
Oh, okay.
Okay. Yeah.
Yes.
Okay. It's fine.
It's fine. Okay. Oh, sir. Okay, fine. Okay, so maybe we can go ahead and we obtain the normalization. So let's look at the gamma matrix algebra. Okay, so this is where we kind of do a little bit of Lorentz algebra thing. Of course, we won't do Lorentz algebra. We'll just say how gamma matrices would transform. Okay. So far we have considered 4 gamma matrices, and which we denoted as gamma mu. Okay, and they were written in terms of Pauli matrices sitting off diagonally 0 sigma I minus sigma I 0, and gamma 0 was diagonal with identity and minus identity sitting diagonally. Okay, So these are the only four matrices, gamma matrices that we have used so far. Okay, and one can check that under Lorentz transformation, these gamma matrices would transform like contravariant vector. Okay, so remember, Lorentz transformation matrix is just a matrix of constant entries, right? Lambda, mu, nu kind of stuff. You can check that lambda, mu, nu acting on gamma, mu will produce a gamma, nu for you. Okay, so it transforms like a contravariant vector in that sense. Okay, now we already know that gamma matrices satisfy the Lorentzian space Clifford algebra. By that I mean that the anti-commutator of gamma mu with gamma nu would give you eta mu nu as against say delta mu nu, okay, because of the Lorentzian signature, but it satisfies that kind of Clifford algebra. So we know that, okay. But the thing is that the Clifford algebra tells you that gamma matrices satisfy certain kind of anti-commutation relation. Gamma mu plus gamma mu is equal to something. Okay, either they are zero if mu nu are not agreeing with the eta mu nu, or they would give you uh, something proportional to eta mu nu. Okay, but the Clifford algebra has nothing to say about the commutators of gamma matrices. So instead of taking the anti-commutator of gamma mu and gamma nu, suppose I look at the commutator of gamma mu and gamma nu. Okay, if you do that, Clifford algebra is not telling you anything. Okay, all it can tell you is that if you write down gamma mu gamma nu, okay, and if mu is not equal to nu, suppose, okay, now of course that is what you would want, because if in the commutator you write down gamma mu and mu is same as nu, then that commutator is zero anyway, right? Every matrix commutes with itself. Okay, so when you write down a commutator gamma mu, you are choosing mu not equal to nu, and if mu is not equal to nu, then let me kind of show you this relation. When mu is not equal to nu, then gamma nu is minus gamma mu, right? Because this bracket is anti-symmetric, right? Or rather, this bracket is symmetric. So it tells you that gamma nu plus gamma mu is equal to 0. Why 0? Because I am looking at mu not equal to nu. If mu is not equal to nu, eta is 0. So that tells you that gamma nu is equal to minus gamma mu. Okay, that is what the anti-commutator tells you. So if you look at the commutator, gamma mu with gamma nu, then you would get a term which is gamma nu minus gamma mu. Now this minus gamma mu can be written as gamma mu itself. Okay, so therefore it is just the commutator of two gamma matrices is just product of two gamma matrices. That is what I wanted to say. Okay, so suppose you write down gamma matrices. Okay, then you could write down gamma mu nu, which is a commutator of gamma matrices, gamma mu nu. Okay, then this quantity is just essentially a product of gamma mu with gamma nu. Okay, that is the reason why I put the factor of half here, because if you use this anti-commutation relation to simplify this commutator, you will get a factor which is 2 times gamma mu times gamma nu. Okay, so gamma mu nu would be therefore defined as a product of these two fellows. Okay, so factor of half is because just to take care of this factor of 2 that would appear by coming from this anti-commutation fellow. The factor of I is used to ensure that gamma mu nu is Hermitian. Okay, so I shouldn't say it is always Hermitian, but it has kind of, if you look at specific components like, you know, either mu or nu is 0. Okay, of course both cannot be 0, but either mu or nu is 0, then it is Hermitian. And if one of them is or if both of them are special component, then it is anti-Hermitian. Okay, so that is the original gamma matrix behavior. If you want to maintain that kind of behavior with gamma mu nu, then it is good to keep a I factor here. Okay, so that is kind of convention. You may choose not to have it and have different hermeticity property for gamma mu nu, which is fair enough. Okay, you could also do one more thing, and that is you can write down gamma mu, gamma nu, gamma rho, okay, and anti-symmetrize in mu nu rho indices. Okay, that is what is called gamma mu nu rho. Okay, this is just a shorthand notation for this expression, exactly the way gamma mu nu is a shorthand notation for this. Okay, so when I say this, put this square bracket here, uh, all the indices sandwiched between this square bracket are antisymmetrized. Okay, so mu nu exchange is antisymmetric, mu rho exchange is antisymmetric, and nu rho exchange is also antisymmetric. Okay, so in that sense, this is a kind of third rank antisymmetric quantity. Okay, now since I said that gamma matrices themselves transform like a contravariant vector, if an object carrying two contravariant indices would transform like a second rank contravariant tensor. Okay, similarly this seems to transform like a third rank contravariant tensor, and all these tensors are antisymmetric. Okay, now generically tensor could be symmetric, antisymmetric, mixed symmetric, it may not have any symmetry property, all kinds of stuff can happen. Okay, but in this particular case, gamma mu nu is explicitly antisymmetric in mu and nu, and gamma mu nu rho is explicitly antisymmetric in all three indices. Okay, besides that, we can write out one more gamma matrix, and in 4 dimension it's a convention to call it gamma phi. Okay, gamma phi is a product which is I times gamma mu, gamma nu, gamma rho, gamma sigma times epsilon mu nu rho sigma. Now remember, epsilon mu nu rho sigma is a Levi-Civita tensor which has a property that if mu nu rho sigma are all different, for example, they are like 0, 1, 2, 3, then epsilon 0, 1, 2, 3 is equal to 1. Okay, and epsilon mu nu rho sigma is totally antisymmetric in all its indices. That means if you exchange mu nu, or if you exchange nu rho, or if you exchange rho sigma, or whatever, under every exchange of indices, it flips sign. So therefore, if you choose epsilon 0, 1, 2, 3 to be plus 1, then under even permutation, that means under any even number of exchanges, epsilon would be positive. Under any odd exchanges, that means you exchange once or 3 times or 5 times or something, under those exchanges, it would be -1. And anytime any of the two indices take same value, epsilon would just vanish. Okay, a quantity like that ensures that gamma phi is effectively I times gamma 0, gamma 1, gamma 2, gamma 3. Effectively, that is the value. Okay. Now, in some sense, we have exhausted all possibilities that we could write down, because we have written down a quantity which is a vector, which is gamma mu. Then we have written down 2 gamma product antisymmetrized. We have written down 3 gamma antisymmetrized product, and we have written down 4 gamma antisymmetrized product. In a 4-dimensional space, you can only have 4 index antisymmetric object. If you write down a 5 index antisymmetric object, then that object is manifestly 0, because you have only 4 values for the indices, and if you have 5 indices and they are all antisymmetrized, then at least one of the index has to be same as one other. And if that is the case, then it cannot simultaneously be totally antisymmetric. So 5th rank antisymmetric tensor in 4 dimension is manifestly 0. Okay, in fact it doesn't exist. Okay, so what we have written down is a complete list of antisymmetric tensors. Okay, if you write down symmetric tensors, then those symmetric tensors are reducible because of the Clifford algebra. If you write down gamma mu plus gamma mu, it would look like a symmetric object, but that would reduce the rank, because that is proportional to eta mu nu, and therefore that quantity is not written in terms of gamma matrices. Okay, these objects will be useful for you when you do particle physics course, because some of the important forces are based on what kind of interactions these particles have. Okay, and these gamma matrices will play important role. Okay, fine. Now remember that we have written down gamma mu nu rho. Okay, now if you have a quantity which is a third rank antisymmetric tensor in 4 dimensions, okay, then there is one thing that you can do with it. Okay, and that is you take gamma mu nu rho, which is like this, and multiply this entire equation by epsilon mu nu rho sigma, okay, and use the Einstein summation convention. That means whenever the index is repeated, you just sum it. Okay, so if you multiply this by epsilon mu nu rho sigma, then mu, nu, and rho are summed. Okay, and therefore that summed indices are not free indices. Okay, that effectively gives you an object which actually carry only one index. Okay, so a third rank antisymmetric tensor in 4 dimensions is effectively behaving like an object which has only one index, which is like a vector. Okay, let us see what kind of vector is this. Okay, but is this point clear that if you have a third rank antisymmetric tensor in 4 dimensions, it would behave like a vector? Okay, so let's do it once again. What we can do is the following, that I have chosen gamma phi in a particular fashion, and it has, and this factor of I exactly the way I have put a factor of I here, the factor of I have put here to ensure that gamma phi squares to plus or minus 1. Okay. Okay, so I don't remember exactly, it will give me plus 1 or minus 1, but if I put a I, then gamma phi would have eigenvalues which are plus or minus 1 and not plus or minus I. Okay, so in that sense, it is a Hermitian object actually. Okay, fine. Now, suppose you are looking at this triple product, okay, gamma mu, gamma nu, gamma rho. Okay, then what you could do is you can multiply this by gamma sigma square. Okay, now gamma sigma square could be a plus or minus 1 depending upon whether the sigma is time component or space component. Okay, so that would make us worry about whether we should put a plus or minus sign here, but let's not worry about it right now. But 1 is equal to gamma sigma square with up to a sign plus or minus. Okay, now then you see that you have a gamma mu, gamma nu, gamma sigma, sorry, gamma mu, gamma nu, gamma rho, gamma sigma times gamma sigma. Okay, you can use the first 4 gamma matrices and convert that into gamma phi. Okay, and then you are left with a single gamma matrix with index sigma. Okay, so therefore gamma mu, gamma nu, gamma rho object can be written as gamma phi times gamma sigma times epsilon mu nu rho sigma. Okay, fine. So in other words, what I'm trying to say is that this object can be written as gamma mu times gamma phi. Okay, or gamma sigma times gamma phi, the way I described it. Okay, fine. Is this point clear?
Yes, sir.
Okay, great. Okay, so what we'll do now is try to understand what these objects are. Okay, so let's do a bit of a counting. Okay, we are in 4 dimensions. We have already written down gamma mu. Okay, gamma mu are 4 matrices. That means mu take 4 values, so there are 4 such matrices, right? Then we have gamma mu nu, okay, which is anti-symmetrized. So if in that, if mu takes 4 values, then nu can only take 3 values, right? Is that okay?
Yeah.
Okay, so mu can take 4 values, nu can take 3 values, but because of the antisymmetry, only half of them are relevant. So you take 4 into 3 by 2, okay, right? Because under the exchange, you get only a minus sign, okay? So therefore, there are 6 gamma mu matrices, okay? Let us list them. Gamma 0, 1, gamma 0, 2, gamma 0, 3, gamma 1, 2, gamma 1, 3, and gamma 2, 3. Okay, these are the 6 matrices that you can write down. Okay, so we have found 4 gamma mu's, 6 gamma mu gamma nu's. Okay, you can easily check that these are, since we can write them as gamma mu gamma phi, they are also 4. Okay, and the gamma phi is a unique matrix. Okay, so if you take the sum of all these fellows, you get total number of 15 matrices. Okay, 4 here plus 1 5 plus 6 11. So okay, plus 4 coming from gamma mu. Okay, so total number is 15. Okay, what we will do is we will add one more matrix which is not part of this story, because these are all matrices which have the property that they satisfy this kind of algebra in the matrix form, not with the indices, but in the matrix form they are satisfy anti-commutation relations, and they have a property that they have plus or minus one eigenvalue, and they are traceless. Okay, we are going to add an identity matrix to this, a 4 by 4 identity matrix. Okay, such that total number of matrices would be 16. Okay, fine. If the reason for adding the identity matrix is that, I mean, it will become clear in a moment, but one of the reasons for adding the identity matrix is that it forms a closed algebra of these matrices, because if you square these matrices, they are proportional to identity or minus identity. Okay, so therefore, if you include identity matrix, okay, that's like including the identity element, it just gives a closed algebra. Okay, so what you find is that the Clifford algebra with an identity is basically, if you are looking at d by d matrices, then it is basically total number of matrices are d squared. Okay, we have 4 by 4 matrices, and that's why we have total number of matrices are 16. Okay, of which 15 of them are these gamma matrices, and one is the identity matrix. Okay, fine. Now, if you try to write down these objects, all these things. Okay, so maybe I can write this stuff down now. Yeah. So if you look at these objects, now remember these objects were constructed. From the 4 by 4 matrices that we had written down. Okay, which are like off diagonal sigma I is minus sigma I, and diagonal identity minus identity. Okay, those were gamma I and gamma 0. Okay, use those matrices and just construct these matrices. These are just new 4 by 4 matrices. Okay, and there's 15 such guys. Okay, when you write them in the matrix form, then there is nothing to choose between one matrix representation versus another matrix representation. For example, you could have written down a matrix which is not off diagonal sigma minus sigma, but it is off diagonal sigma sigma, the way alpha matrix was written. Okay, you could have chosen it in that fashion also if you wanted. Okay, maybe a overall factor of I sitting outside, but the matrix has symmetric sigma sitting around. Okay, you could have chosen that also. Okay, now all these are 15 different ways of writing these 4 by 4 traceless matrices with eigenvalue plus or minus 1. Any 4 of them could be used to write them as gamma mu. Okay, there is nothing very special about any choice. Okay, so that is why there is something called a Dirac basis. Okay, Dirac basis is the one which we talked about just now, that the gamma matrix is off diagonal sigma minus sigma, and gamma I, whereas gamma 0 is diagonally 1 minus 1. Okay, nothing special about this except the fact that in a particular problem, for example, taking non-relativistic limit, this basis seems to be good. Okay, but you may be interested in a different kind of problem. Okay, you may be interested in some particle physics related issue where you are looking at a specific kind of particle in which this basis may not be the best basis. Okay, you could choose any of these matrices and call them gamma mu. Okay, so there are different choices. Like for example, there is a choice called I think this called Majorana basis. Okay, that is a basis in which all gamma matrices that you write down, all gamma mu's are purely imaginary. Okay, all entries in the matrix are purely imaginary. Okay, that is just a specific choice out of these 15 matrices that he picked. And if you do that, then remember your Dirac equation has a I h bar times something or other, right? Either del del t or alpha dot del or some such thing. If you choose your gamma matrices in such a way that they are purely imaginary, then that imaginary piece will kill that I factor, and your equation would effectively become real. Okay, that is the technique that he exploited at some point to study solutions to Dirac equation. Okay, but so it depends upon what problem you want to solve would help you choosing an appropriate basis. Okay, but they are all out of these 15 matrices. Okay, fine. Okay, so as I said that gamma mu transforms like a contravariant contravariant vector. One can check that gamma mu nu would transform like a second rank antisymmetric tensor, contravariant antisymmetric tensor with respect to Lorentz transformation. Okay. On the other hand, gamma mu nu rho, which can also be written as gamma mu gamma phi, would transform like what is called a pseudo vector. Okay, I'll explain it in a moment. Okay. This is kind of easy to understand if you understand the fact that gamma phi transforms like a pseudo scalar. Okay, so so identity, for example, which is the 16th element, would transform like a scalar because you do a Lorentz transformation, nothing happens to identity. Okay, so that's what one means by a quantity which is called a scalar. Okay, what is a pseudoscalar? Well, pseudoscalar is a quantity which does not transform under Lorentz transformation exactly the way the scalars would. Okay, only difference is that if you look at the discrete transformations in the Lorentz group, in the inhomogeneous Lorentz group, then you have transformations like parity transformation, x vector going to minus x vector, or time reversal transformation, t going to minus t. Okay, in under those transformation, a quantity which is called scalar if it does not change sign. Nothing happens to scalar under that transformation. Okay, a quantity is called pseudoscalar if it changes sign. Okay, so let's try to go back and see what happens. Okay, oh sorry, it's right here. Okay, so we have a gamma phi written out here. Okay, and as I said, this gamma phi is a kind of covariant way of writing it. Okay, but imagine you have taken mu nu rho sigma to be 0, 1, 2, 3. Okay, and 0, 1, 2, 3, for 0, 1, 2, 3, epsilon is equal to 1. Okay, or minus 1, doesn't matter really. That is not very important, but at least it is non-zero because all entries are different. Okay, so let's choose that to be 0, 1, 2, 3. In that case, we know that epsilon is non-zero. If it is plus or minus 1, it will just make it plus or minus I here. Okay, that is not really of any consequence. What is important is this, that this will become gamma 0, this is gamma 1, this is gamma 2, and this is gamma 3. Okay, now you look at this quantity and say that you want to do a time reversal transformation. Time reversal transformation would say that anything which has a 0th component will flip side. Okay, in that case gamma 0 will go to minus gamma 0. Okay, whereas gamma 1, gamma 2, gamma 3 is not affected. Okay, and if, because of that, gamma phi will go to minus gamma phi. Okay, so therefore gamma phi, in spite of not having any space-time index, is not exactly a scalar, but it is a pseudoscalar because under time reversal it flips sign. Okay, you may say that like, okay, let's try to check what happens with parity. Parity transformation is x vector going to minus x vector, means x1 goes to minus x1, x2 goes to minus x2, x3 goes to minus x3. If you do that, then gamma 1 flips sign, gamma 2 flips sign, gamma 3 flips sign. 3 sign flip would again flip the sign of gamma phi, and therefore gamma phi will transform to minus gamma phi under both time reversal and parity transformation. Okay, so I have been saying this, but I just get a feeling that have you people discussed the time reversal parity somewhere in quantum mechanics earlier?
For the Cramer's rule and symmetry, that in quantum mechanics 1 we did something.
Oh yeah, that's right. Okay, so at least you know the parity thing of the state, right?
Yeah, somewhat, yeah. As symmetries we did like study them. Yeah.
Yeah, Because when you study symmetries in quantum mechanics, you must have studied parity and time reversal symmetries, right?
Yeah.
Yeah. Okay.
So one thing here.
Yeah.
So we are writing things like gamma mu nu transforms like an antisymmetric tensor.
Yeah.
That is not like I mean, we aren't stipulating that, right? It just turns out that if gamma mu nu and there was some lambda mu rho and lambda nu sigma,
Yeah.
that itself could be another representation for gamma matrices.
That is right. Yeah. So since
It's
gamma,
turning out to be that way. It's not like we are stipulating this to be a
no. We are not. We are neither postulating it nor defining it. We are trying to show how it transforms, given the fact that gamma mu transforms like a vector. Once that is used, then you can derive all these results from there.
I mean, even gamma mu's transformation as a vector, it's simply like gamma mu, lambda mu nu would be another representation for the
Gamma
entire
matrix.
anti-commutator relation.
Exactly. Yes. Yeah. So you don't have to kind of postulate it. Okay. But what I'm saying is that, like, even if you use that as a definition for transformation of gamma mu, rest all are derivable from there. Okay. Okay. So I think I have already overshot this thing. So I can stop at this point and we can pick it up from here. Okay. So what I'll do is, like, maybe I'll modify this part of the discussion, add a little bit of discussion about parity, time reversal in it, so that these arguments become a little more transparent than what I have. Okay. And I would have kind of improvised on the board right there, but here it is like I'll have to type it actually. So, but I think in the next class, I'll probably kind of include these pieces. Okay. Okay. Any questions?